All right. So today I want to talk about inclined planes and basically ramps. Don't think too much about it. So let's start with a screen share and show you the type of problem that I'm thinking about. All right. And remember, at any time, if you want, you could ask Jay questions or you can ask me.
I want to do it.
Somebody's got a mute there. Oh, right on. That's cool. Thank you for hitting the mute. Appreciate it. All right. So, whoops, not there. It happens to all of us. So, in this case, I want to look at this problem right here, 5.9. All right. Now, you're going to see a lot of zombies in this chapter. I don't know. For a while, I was really on a zombie movie kick, and that happened to coincide with when I was writing these problems. So, there's a lot of problems with zombies. Okay, so I'll let you read that. I'm going to, and notice this is one of many problems where we see two different angles. So that's a theme over the last couple of class periods. Remember to tell the difference between different angles. You won't always have just one angle in a problem. I know that seems cheesy, but it's worth emphasizing. Okay, I'm going to draw this picture up. Will you draw up what you think? And notice this is going to be difficult. So you could try to draw what you think the FBD should look like, and then I'm going to actually draw that one with you. So do what you think the FBD should look like. And I'm just going to get the sketch, but I'll wait to do my FBD until we're all watching together. Oops. Get that out of there. Okay. Hey, can you guys hear me again? Could you? Oh, sorry. Could you guys hear me now? Okay, cool. My Zoom was doing something weird there, and my computer locked up. I'm sorry about that. All right. Well, hopefully you've had a chance to look at this problem now. So I'm going to go ahead and get it on my page. All right. So you've probably drawn an FBD or tried, and you might have realized, wait a minute, this is not so easy. And that was what I wanted to point out. There are some tricks to learn for this type of problem. The first trick I would recommend is I'm going to draw this problem with a small angle. I don't know if I've said this to your class or not, but generally speaking, when I draw figures, I try to avoid 45-degree angles like the plague. The reason is it makes it easier for me to visualize, is this angle right or not? Let me give you an example. We have a block sitting here. Okay, and I think I said this angle is theta, right? Let's get this over just a little bit. Yep, that angle's theta. Okay, so now in this case, there's going to be a normal force. Does anybody remember which way the normal force points? What's the best way to describe the direction a normal force points in general?
Perpendicular to the ground.
I can't hear you at all. My headphones. All right. I think, hold on. Let me check something. Oh, I see. Okay. My headphones dropped out. All right. That's what it was. Zoom. Okay, you can still hear me? All right.
Yeah.
Oh my gosh, my headphones, like, I don't know, the USB port was janky or something. So hopefully you're not getting a lot of echo. My apologies if you are. I'm going to get through this problem and then worry about the headphones after that. Okay, so what did you say for the normal force? I'm sorry.
Perpendicular to the ground.
Perpendicular to the surface. So in this case, it's that direction is going to be the normal force vector. Does that make sense? If it's sitting on a ramp, the ramp is pushing this way. Let me give you an example. Well, okay. Let me do this. Right? If you have a book, let's go this way so you don't have to see all those pages, right? And you put something on top of it, right? The paper is going to push perpendicular to its surface. So notice it's pushing this direction, not straight up. Again, it's pushing perpendicular to the surface. And I can tell this is true because if I turn it too much, it tends to fall over because there's a component. All right, more on that in a minute. We're actually doing that problem. So let me get there in a minute. Now, which way does gravity act on an object?
Straight down.
Straight down. So that, and actually it acts right at the center of the object. So that would be mg. Here's a cool trick. When you're drawing the arrows and you don't know what's going to happen with all the angles, sometimes I'll put the size of the force at the arrowhead. That way, if I need to draw stuff over here or here, I haven't taken up space on my paper. All right. So in this case, isn't there a zombie pulling on it as well? So there's a zombie pulling this way, and I think I called the size of that force capital T. So that is actually a correct FBD. Generally speaking, we usually say which way it's accelerating. So let me take a look. I closed my page. Sorry about that. Just getting my picture back up. Oh my God. All right, so I think I called it T and Phi. All right. I'll put this down under here just in case. So in the picture, I actually labeled this angle right in here as phi. And we're keeping distinct phi, which has the near vertical versus theta. All right. And then, was this thing accelerating or not? Does anybody know? Did it give us a clue? I'm going to reread myself. What do you think? Accelerating? Yes, no?
No.
No. What's the key word?
It has a constant speed.
Yep. Now we can do this any way we want. We can draw the coordinate system any way we want. We've already discussed that coordinate systems shouldn't affect the final answers. So this part's kind of interesting. What is the best, or what is a coordinate system you might think of using? There's the classic XY. Can anybody think of another one?
Kind of tilted to fit the ramp.
Tilted to fit the ramp, maybe like this. That turn, whoops, maybe like that, if I could draw my hands. So I would actually draw this as the X direction and this as the Y direction. The reason is it makes it easier to split up the forces. It's also standard procedure. And finally, it turns out, while you might not notice this, it actually relates a lot to circular motion too. So later on, when you get to a chapter on circular motion, it really helps to understand how things work if the coordinates get rotated. So there's a number of reasons to do this. Primarily, because it makes things standard and it helps us with circular motion. All right, let's keep going. So now, this is kind of messy, because there's so many lines. There is one thing I want to get out of this before I redraw it. What's this angle right here where I put a green dot? What's that angle? What's it look like?
90
90
degrees.
degrees.
90 degrees. So what's this angle right here where I just put another green dot? This is 90. This is theta. What's
90
that?
minus theta.
90 minus theta. Remember, all the angles in a triangle add up to 180, right? So that's 90 plus theta plus the green dot. Well, if I do this, that's going to be 90 minus theta equals the green dot. So this angle up here is 90 minus theta. Sorry, that's so small. Can you read that? I hope so. If you can't read it, just unmute. I'm going to assume you can read it unless you holler at me. Now, look at this pink coordinate system. We're trying to split things up this way now, right? So, oh, I forgot to mention constant speed means A is equal to 0. Let me write that in my coordinate. You guys said that already. Sorry about that. So now take a look. What's this angle with this pink dot? Maybe I'll give you another hint. What's this green dot right here? What's this one supposed to be?
90.
90, because it's from the normal force, which is supposed to be perpendicular to the surface, right? I'm trying to draw it perpendicular and I keep screwing up. We're drawing at an angle. Is that pretty close? It's pretty close. And let me straighten this one out. Hopefully that looks a little bit closer. All right. So somebody just said this angle's 90. Right? Maybe I'll draw the right angle symbol. So what's the pink dot? What's left for the pink dot?
So should that one be 90 minus theta? Like minus that angle? That
What's the angle from this line all the way over to that line?
180.
180. So let's do the math. I have 180 minus 90 minus, or whoops, 180 should equal 90 minus theta plus 90 plus the green dot. Let's call this green triple dot, just so it's different than the other ones in the video. So this green triple dot plus this angle plus that one should add up to 180, right? So in this case, notice 90 plus 90 is 180. You actually get theta. Or think about it this way. Don't these two angles have to add up to 90? If this is 90, that means this is 90. Sorry, I'll use my marker. If this is 90, that means this angle right here is 90. So that plus that have to add up to 90, which means the only way that works is if this is also theta. So far, so good? You can go through this again later or draw it out on your paper. It helps to draw large pictures. If you drew this one pretty small, you probably know what I'm talking about. We're going to redraw it in just a second. Another piece out of this, we're going to use the pink coordinate system as my x coordinate. So before you draw anything, we know we need to split up these. N is on the coordinate system. T is pretty much already split up. We can see that one. MG is the tricky one. So I want you to think about this. I know that one of the components comes down this way. Now I'm going to draw 3 possible choices that students sometimes draw, and I want you to tell me the correct one. So there's this, and there's this. Oops, that's a little off. So there's choice A, B, or C. Which one do you think looks most correct for splitting up the components along the x-axis? Remember, the x-axis is now like this. So is it A, B, or C? What do you think?
A.
A, notice A is the one parallel. So students oftentimes draw B. B looks correct. I'll just show you B and why it's incorrect. A lot of times I see this on students' papers. Well, this can't be correct. Notice the hypotenuse has to be the original vector. We're splitting up the original vector into smaller pieces. Well, this shows the vertical component is larger. That can't be correct. So we see that that was not correct. The idea is your component has to be parallel to the x-axis. You wouldn't believe it, but I see this every year, dozens of times. So we've got to be careful. All right, now we're ready to go. This is really all the pieces we need. So let me ask you here. We see two components here. I know that the size of this vector, I'm going to get rid of some of these lines now, and maybe I'll get rid of this just so it's not so busy. In this case, the size of this is mg. So what's this component going to be? Is it mg sine or is it mg cosine of theta? This side right here.
MG sine.
mg sine, good. So I'm going to move this up here now that I know where I need to write. How about this side then? That's going to be the other one. Over here, this one's pretty easy. So notice what's this side going to be right here? Is it
MG
t sine phi or t cosine?
T cosine.
T cosine, adjacent to phi. So katoa, cosine's got adjacent, this is adjacent. So that means this one up here is going to be t sine phi. And now we've actually split this thing up. This picture is pretty darn messy on your paper, probably. So why don't we redraw it and actually make a true free body diagram? This was not technically a free body diagram because I had the ramp in there. A free body diagram shows only one body, the box. I actually drew two, the box and the ramp. And I did that so that we could understand this angle. So don't erase any of your work, make a second picture and make it frickin' big, like a quarter page to a half page, so you have room to squeeze all this in. So for me, I'm just going to start down here and do it again. All right. Actually, yeah, I'll just do it up top because I'm going to need this room to do the work later. So you got your picture on your paper. Take the time to do this one right. It happens so often in physics. You've got to be an expert at this particular drawing. Okay. So I'm going to draw the box as a dot to simplify it. I know that mg is going to point straight down. And I know we just talked about this. This is mg sine theta. This is mg cosine theta. I had a tension over here. I think it was at some weird ass angle. That's a technical term. This angle was phi. We discovered that this angle was theta. And the normal force pointed this way. And this figure is not to scale, but finally, it didn't really matter, but we could say that this direction is the x direction. This direction is the y direction. Okay, and we said that acceleration was 0. And I hope that looks a lot cleaner than the last picture. So there's no crime in drawing multiple sets of the same picture just so you don't screw up. That's totally legal. All right. Now, from here, it's a lot easier to proceed. But before we go on, are there any questions about that?
Is it okay if we drew the free body diagram to fit the X and Y axis? Like
So
if
a
we
common
tilted
thing
the
that
whole
people
picture?
do is they'll say, oh, I'm going to redraw this, and then I'm going to redraw this. And I'm purposely making a mistake here to see if you catch it. Some people will redraw it like that, where they say, well, now it's on the XY axis, right? So they literally rotate the figure in your mind and then try to draw it. Does anybody see the mistake I made?
Yeah, you put MG on the opposite side of that.
And that's why I don't recommend it, because I see students do this all the time on test day. They get in a hurry and they accidentally screw up. MG should be rotated this way, right? So the idea is if you tip it all in your head, you could do this and say, well, doesn't this look right? I don't recommend that for two reasons. One, the error I just showed is very common for students on test day. They'll flip the MG when they're in a hurry because they're not paying attention, right? It's one. The other thing is, I think it's more physically meaningful to show pictures of the arrows in the directions they actually point in the real world. And this is useful, again, particularly when we get to circular motion later. Maybe not so much for these problems. So the short answer is do whatever you want as long as you get it right. But I recommend this way, and all the answers in my book are done this way, where I draw the forces the direction they actually point in the real world, because I think that gives you practice. Is that good?
Yeah, perfect. Thank you.
Yeah. It's definitely a good method that a lot of students learn in high school, but I think there's going to be a time when you just don't want to do that anymore, and it's coming sooner rather than later. Certainly when you get into engineering homework, it starts to make a difference. So that's what I would say about that. Good question. Others? Yeah. If you're wondering why students make that errors, it's because sometimes ramps go this way and that way, and then they get in a habit. Maybe they do 2-3 problems in a row where MG's this way, and then the ramp switches, and then, oh, whoops, they forget to switch MG. When you do it in situ, in the situation it's applied, you don't make that error. Here's another thing I wanted to point out that I don't know if I made this big deal about drawing skinny angles, right? Check this out. If you draw angles that are deliberately not like 45, significantly different, watch how easy it is to get the MG. You draw this arrow, you know you got to split it up perpendicular. You look at it. Theta is less than 45. Which of these two angles is less than 45? Is it the single dot or the double dot?
Double dot?
Single. What double?
Double, right? Basically, what I'm saying is, which of these two angles looks like theta? This one, right? It's about the same. So if you draw everything at 45 degrees, you can't do that check. So by deliberately drawing the angles at less than 45, you can be like, oh, clearly this isn't theta. It's much bigger than theta. This must be theta then. So it's kind of a cheat to get your way through this without having to do this, oh, 90, this, that. By drawing the skinny triangle, you can just see right away that's theta. And this works whether the ramp's going that way or this way, because in different problems, the ramp changes. And so it's always tricky to think which one's theta. Just having this angle be small makes it harder to screw that up. All right, let's do the sum of forces. I'm going to do the sum of forces in the X. Somebody tell me one force in the X direction. So again, if you don't remember, we're doing sum of forces equals mass times A in the X. Okay. What's one force in the X direction from the arrows?
T cosine.
T cos. According to this coordinate system that I chose to draw, is it positive or negative T cos?
Positive.
Yep, because it's going up the hill. So T cos phi. Next, somebody else, another force in the X direction. Or are there any? Are we all done?
MG sine theta.
MG sine theta, positive or negative according to the coordinate system I drew?
Negative.
Negative. Excellent. Any other forces in the X direction? I think that's it, right? These two are the only ones that match up to that x-axis. So all this, in this particular case, is equal to what?
Zero.
0, because A happens to be 0. Got it. All right, let's do the y direction. So give me a force in the y direction. Tell me if it's plus or minus. Let's rip it out. Anybody that wants to.
Mg cosine theta.
Mg cos, plus or negative?
Negative.
Nice. Mg cos. What's next? Somebody else. If you've already spoken up, you can speak up again. We've kind of gone through most of the list here.
Natural force?
Careful, I would call it normal force. Remember, normal means perpendicular in math, so try to remember it that way, normal force. Is that cool?
Yeah, sorry. I just had a physics teacher in high school that always called it natural, so it's kind of stuck with me a bit.
Yeah, I've heard that many times. So I like to think normal just because it reminds me perpendicular, which I think is the more important thing to remember. Really, what does it come from? Right? What keeps this marker from entering my hand and my flesh? Electrons. It's really an electric force, right? All of these molecules in your hand have electrons in them on the outer shells, and so do this marker. So, right, electrons don't want to go through other electrons. So really, it's like we could call it an electric force, but we're not going to do that. So let's call it the normal force because that's the primary. Yeah, my bad. Well, I think of chemistry basically as applied physics. So, touche. All right. So, if you didn't know, Jay's a chem major. So, all right. Okay. Where are we going? Okay. So we got what's the other one? Is there another one? Or is that it?
There's a T sine P. Phi. Whatever.
And it's positive, agreed? Well, I
Yeah.
already wrote it. It is. All this one, again, A is equal to 0. Let's not think too much. So that's the hard part of every physics problem. Drawing the picture correctly, splitting up the force vectors correctly, making sure you don't screw up theta and phi or sine and cosine. Look at this. There's a cosine. This is very common to have mixed sines and cosines and angles. So that's why I've been deliberately being a jerk about sometimes putting the angles to the vertical, just so you're always watching for it. Here's a case where naturally it shows up based on, it started out as an angle to the horizontal for the ramp, but it ends up as an angle to the vertical. There's nothing you can do about this. And it actually is faster to remember geometry than to remember trig identities, in my opinion. Yeah, that said, okay. So on a typical problem, let's say this was an 11-point problem. 1, 2, 3, 4, 5, 6, 7, 8 points right here on a paper test. It's literally most of the points for these types of problems are, can you draw them correctly in both the X and the Y, right? And can you get the force equations correct in the X and the Y? So think, if you can't do this, you will fail these questions and you will not succeed. That said, most students usually think, wait a minute, I actually can do this better than kinematics and projectiles, which after you do this for a couple of weeks and you go back and look at projectiles, you're like, wait a minute, now I can do projectiles too. How did I miss these? It's weird. This happens every year. By the time you finish the semester, you look back at the beginning, you're like, oh man, that was so easy. How did I screw that up? Well, that's just because you were learning. So don't beat yourself up. All right, that said, since this is the hard part, let's go look at the answer and move on. So I want to focus most of my time with you on the setups. So let me do this. Let me see if there's anything I missed. Okay, so that was that. Okay, and so from there, we're supposed to get the tension, magnitude, and the magnitude. So we're supposed to basically solve those equations for T and N. So let's just take a look here. Most of the time, this is what happens. We have two equations. The maximum number of unknowns you can solve for is 2. So one of these things is solve for t. The other one is solve for n. Notice, which one should we do first? Which one's easier to solve for, t or n in this problem?
T.
T, which equation would you use, x or y?
X.
Yeah, and once you get t, how could you solve for n?
You just plug in T in the
Just shove
Y
it
equation.
in, solve for n, good to go. Now, there are different ways to do this. Here's some advice. Usually, I would solve for n before you plug in. The reason is, once you plug in, it's more shit to write as you move it around. So this is a trick that you see pretty soon in physics. You're like, wait a minute, the order in which I do my algebra can make my life easier or harder. So think to yourself, you're like, when I solve for t, that's going to be a big mess. So why don't I solve for n first, then plug in t? Now, that said, either way is going to work, and it's not that much harder. So let's go look at the solution, see if there's anything interesting there. Oh, before we check that, okay, let's say I get t, and let's say I get n. Tell me something you should do after you get the answer to check it. Check the
Units.
units. Excellent. And then you could even go further and do other things like what happens if the angles go to 0, or what if. Now, that's really the physics. What if or why? So when you find yourself asking those kinds of questions, you should start crying, because that means you're becoming a physicist and there's something wrong with you then, right? So if you find yourself asking, what if this happens, or why is that happening? That's a good sign for passing a physics class, but a bad sign for your life and your societal status. All right, let's go look at the, that's my attempt to make a joke. Let's go look at the solution and see if there's anything in there. Okay. Oh, 510. Wait, what were we on 510 or were we on a different one? I think we were doing this one, right? Sorry about that. 5.9. All right. And so I think we got all this. There I did the algebra. Notice what I did here is first I solved for n, then I plugged it in. And so you get some stuff. Ooh, look at this cool factor. Whoa. That's really weird and fun and exciting. The neat thing about this is, imagine if you are a civil engineer and you're building a ramp that's designed to hold whatever boxes that are being dragged up or something, right, by a robot. This gives you an idea of the maximum. Remember, the normal force is the force that the board must exert, or the ramp must exert upwards on the box. Well, this gives you an idea of how much force will be exerted the other way, back down by Newton's third law. More on that in a minute, or probably next class period. But so this gives you an idea of how thick your ramp might need to be, because you know an idea of how much force it might need to sustain. Or if you know how much force your ramp can sustain, it might give you a limit on how much mass the box could have. So it could give you okay, anyway, the point is, by doing these problems algebraically, you can then answer different types of problems that are actually useful to people, rather than just playing with letters and numbers and having fun. So there is a reason to do this algebraically. It allows you to design things if you do it algebraically. So that's why we're basically never going to have any numbers in these problems. Maybe once in a while in Canvas, but yeah, a lot of times you're actually going to be able to do these problems without any calculator, and that's a good sign. So definitely get the algebra right, the pictures right. Questions before we go on?
So the formula that right above the x and the y, like force things, that just stands for like the sum of forces equals mass times acceleration.
Yeah, this is x and this is y. And I would have written that out, but I run out of room on my whiteboard all the time.
Okay.
Is that cool?
Yeah, I was just wondering what the formula stood for.
Yep. Sum of forces in the x equals, so this is Newton's second law. These are the sum of forces, right? These are all the forces acting on the object. The acceleration is not a force. It goes on the other side.
Okay.
Good?
Yeah.
Right on. Others?
Oh, and
Yeah,
one
go
more
ahead.
thing. So like the reason it's like 0, right, for like acceleration, and the reason like those two things like equal each other, is it because like all those forces just balance out, and like that's why
In
like they
this
balance
case,
each other out?
they balance out. How do we know they balance out, though? The
Because
way we knew was the problem said the words constant speed. Think back to kinematics. If you have constant speed in a constant direction, you have constant velocity, right? If your velocity is not changing, acceleration is 0. And once we know that acceleration is 0, Newton's first law also applies, which says the forces are balanced. So you can think of Newton's first law, which says the forces balance, is valid if you're in motion and stay in motion in the same direction. That's the cases where forces balance. But for me, it's easier just to say, well, Newton's second law always applies. And sometimes acceleration equals 0, sometimes it doesn't. And
yeah, and you could use that for x, y, and z.
X,
Like,
Y, and Z. Now, let me ask you this. How many forces are pointing out of the page or into the page on this box?
no.
Nothing. So what's the net force in the Z direction? 0. What's the acceleration in the Z direction? It's also 0. Sweet. An object at rest in the Z direction stays at rest in the Z direction unless there's a net external force in the Z direction. In this case, there's no external force in the Z. AZ is 0.
Okay.
What do you think? Okay. Let's try looking at the next problem, and there's more geometry. Yay! I actually really like geometry. I'm a weird guy like that. I used to take these math tests when I was an undergrad for fun, believe it or not. Well, I also got free pizza. But yeah, when I took these free math tests, they were really hard, and the only problems I could ever get right were geometry. It was really hard. Have you guys ever heard of the Putnam Exam? No.
No.
Yeah, it's a really tough exam. If you're bored, I used to coach the team. They're not doing it this year because of COVID. It was a long time ago, but I mean, it's seriously difficult. So math professors will take this test and score zeros. So yeah, it's very difficult. Most math professors can probably get a couple questions right out of 12, but most cannot get all 12 right.
What kind of questions are they?
I'll show you in office hours. Because I want to get, yeah, they're really hard.
Okay.
Yeah. Well, so one year there were 10 points each. I'll say it this way. We had a student that was really good at math. And I said, if you're willing to practice 4 times on Saturday and show up to take a 6-hour math test on a Saturday, I will fill out the paperwork and let you take the test. And he said yes. So then I had to do it. And I was cursing myself all semester. This guy scored a 1 out of 120 points. And he was in the 50th percentile. 1 out of 120 was better than half of the students that took the test. This is a nationwide test with students at Harvard, Caltech, Princeton, International. They do it. Yeah. So it's serious, man. Yeah. Frank the Tank. That's what we called him back in the day. All right. Anyways, let's get to work. I'm going to try plugging in my headphones in a second. And usually that locks up my Zoom, but it'll give me better sound. So I'm going to first share the screen and tell you what problem we're starting with. And then my computer will lock up for about 20 seconds or a minute. So let me share the screen. Whoops. Okay. Is it sharing right now? Weird. It's not giving me the border. Hold on. I'm going to try that again. There we go. Now it looks good. So hopefully you can see problem 5.10. Like I said, I'm going to plug in my headphones right now, so my Zoom is going to lock up. Start working on 5.10. Okay, hopefully I'm back live and you can hear me now again. Is that true? Okay, thanks, Jay. I appreciate it. It's funny because I actually turn off the images of you guys so I can actually see the screen while I'm working, but I opened it back up. All right, so in this case, notice the angle is significantly different than 45 degrees. So I'm going to try and draw it that way. All right. So we're going to apply a force F. A force with magnitude F. Okay, it's insufficient to support the mass. It accelerates with magnitude A down the incline. All right, I think I got everything here. Okay, so we're trying to do this situation where we apply a force this way. So it's actually a lot like this board right here. Think about it. There's an angle on here, and what I'm saying is I'm going to put an eraser on here, try to line it up so it's approximately right. So I'm going to put this on here, but what if it's not enough and it starts falling down? So I'm trying to hold the eraser up with the smallest amount of possible of a horizontal applied force, and it's not enough, so it starts slipping down. That's all we're doing. Got it? One last time. A horizontal applied force, it's not enough, and so it's slipping down. That's this problem right here, right? Which way is this thing accelerating? Did it say? I think it said down the plane, right? With magnitude A. So in this case, I'm going to draw the coordinate system again, perpendicular to the plane and parallel to the plane. So that's my X direction. I'm going to shorten this up so it fits better. And the Y direction. So I want to use this coordinate system. Notice you could have said X is going up the plane, but it doesn't matter. We know you get the same answer regardless of the coordinate system you use. Remember, the coordinate system doesn't matter. The elevator problem with the coordinates up versus down, we got the same crap. All right. Now, in this case, I'm going to do what I did last time. I'm going to draw this and get the forces right and learn about the angles. Then I'm going to redraw it as a free body diagram. Okay. So now here's a cool trick that you can do. Rather than have the arrowhead be on the force, a force is a vector. You can move it around. Pushing on the block from this way is equivalent to pulling it that way, right? So what you could do is you can grab this force and actually move it so that its tail is over here. The magnitude is F, the vector is F vector, but together these two form the vector. What's another force acting on this thing?
The normal force,
Normal force. Which way does that point?
perpendicular to the surface.
Okay. So like this, yes or no?
No.
Like that?
Yeah.
Yeah,
something like that.
exactly.
Yeah.
Good. All right. Normally in class, I would say, show me with your hand, but it's a little goofy in Zoom, right? All right. So do we have all the forces?
There's also the force of gravity.
Yeah, I was waiting for you to say that. Oh, ouch. Which way does gravity point?
Straight down.
Yes. Now, I'm just going to exaggerate this so I could see the angle, but whoa, that's terrible. It's funny drawing from the side like this. It's very weird. That's a little better, I hope. So sometimes I'll deliberately exaggerate this one. So this is mg. So now let's figure this out. I need to draw my coordinate system on here, right? And so now, if this is theta, what's this angle in here where I'm pointing? What's that angle? Is it theta or is it 90 minus theta? What does it look like?
90 minus theta.
Yeah. And so then what's this angle right here?
Theta.
Theta. So I'm going to draw that in. And now because this is so messy, I can kind of, what's this angle?
90 minus theta as well.
That's 90 minus. We might need that this time. Do you see that? What's this angle up here? What's that angle?
Theta.
Theta. Notice this pattern. This is a trick that works all the time with geometry, which is why I wanted to show you this problem. Basically, every other angle is theta. Every other angle is 90 minus. I don't know if you remember, we said this was 90 minus theta. So we see every other angle is a 90 minus theta, and you could keep going. What if I drew this upwards? This would be 90 minus. This would be theta. If I kept this one going, this would be 90 minus. This would be theta. And so a trick on these inclined ramps is first draw them in situ with the ramp there and figure out your thetas and your 90 minus thetas. You've got it figured out. Every other one should be theta. If you draw a skinny triangle, it's really fast to see it. The skinny ones in this picture happen to be 90 minuses, and the fat ones happen to be thetas. Got it. Now, I'm going to redraw this. You can actually see this on your page and redraw it. If you want, you could do a quick screenshot. I'm just going to redraw it without the ramp and without all these lines so I could see better. Okay, so if I make a screw up, I'm counting on you guys to help me. There was an MG straight down, and I think we said this angle right here was theta, right? Once I get one of them, the rest should be easy. So in this case, this was MG, and then there was a force straight to the right. I forget what color I used for that. I don't care. There was a force that way, and we said this was also theta right here. Or maybe you use the 90 minus theta, but whatever. I'm just labeling the thetas for just because that's what worked out. And then the normal force was supposed to be this way. And so just lining up my coordinate system and moving it up here so there's room. Sorry, I'm not drawing this perfectly, but you won't either, so you got to get used to it. So in this case, A is going down, and I called it that way X. And I forgot to label this problem. This is 5.10, I think. I hope. All right. So now we're going to do the sum of forces in the X is mass times A sub X. So what's one of the forces in the X direction? Oh, I didn't label them, did I? Okay, let's just go through. What's this arrow right here? Is it F cosine or F sine?
F cosine.
F cos, and then we're on our way, right? And then let's get this one right. In this case, this one is
Sine.
okay. Running out of room there. All right, so what's one force in the X direction? And it's sine. Positive or negative? What do you think? Remember, this is the x direction. Look for an arrow that is parallel to that direction.
F cosine theta.
Okay, according to this x direction, is that going to be a positive f cos or a negative f cos?
Negative.
Negative f cos, I agree. Somebody else, give me another force in the x direction.
mg sine theta.
Mg sine, positive or negative according to this?
Positive.
Excellent. Any other forces in the x direction? If so, what is it and what's its sign? What do you think? Anything else? Yes, no.
I'd say no.
I agree. This one's in the y. We already got those two. So in this case, this is all equal to 0, right?
No.
No. What is it in this case?
It equals a.
Okay, is it MA, M negative A, or which of those?
Positive a.
Positive MA. Now you know why I drew the coordinate system this way. I generally do this. I line up my coordinate system such that A aligns with the x-axis. When I do that, it means I don't have to split up the A vector. Also, notice in this problem, you may be saying, man, we had to split up two vectors. Why didn't I just use the normal right-left? Well, if you had tried to use the normal left-right, you'd have to split up the normal force and the acceleration vector. Most students forget about splitting up the acceleration vector. So you have to split up two vectors, whether you rotate the coordinate system or not. So in this problem, if you don't want to think about figuring out the components of acceleration, which can be tricky sometimes, well, then maybe we do this. All right, so let's keep going.
So I just had a quick question.
Yeah, go for it.
A like represents a sub x right there, right?
In this case, do you agree that A, all of it, is in the x direction?
Oh, yeah.
And that's why we did this. So, well, tell me right now, what's AY based on this picture?
0.
So notice this is the trick. By rotating the coordinate system, one of the equations is at least easy because one of the equations equals 0. So even though this looks like a lot of work, no matter what you do, it's a lot of work. Having one of the things end up equaling to 0 is actually slightly easier and slightly preferable. Is that good?
Yeah, thank you.
Nice. Whoops. So let's do this now. Let's do the other one. Sum of forces in the y is going to, okay, so in the y direction, what's our equation? Somebody give me one force in the y direction.
N.
Positive or negative according to this coordinate?
Positive.
All right, N is positive, I agree. Next, somebody else, something else.
F sine
F
theta.
sine, positive or negative according to this?
Negative.
Exactly, ooh. So you're kind of pushing it down into the, okay, that's cool. All right, and then, oh, so that's supposed to be a letter S, isn't it? Right there, sorry about that. Okay, anything else or are we done?
mg cosine theta.
Correct, mg cos. Positive or negative according to this?
Negative.
Yeah. So in this case, it's going to equal MA, right?
No, it equals 0.
It equals 0. So all of the acceleration was in the X. I was trying to trick you. I couldn't. You guys are too good. Does that make sense? All of the acceleration is in the X. That's why we put the A, all of it, in the X, not a cosine, not a sine. And then none of it is in the Y. That's why this one's equal to 0.
if
That's 2/3 of the problem right there. Oh, go ahead.
so if we hadn't flipped the coordinate system, it would be like a little bit mixed, right? Like between the
Sure.
acceleration A and X.
What is our goal in this class, do you think? We're trying to learn, right? Do you want to see it and try it and see what would happen?
No, I could probably guess. I was just asking, like,
It'll only take me 10
this just
seconds.
made it a lot
if you
easier,
want.
right?
Yeah. So
Yeah.
I think it's worth it to see it, is what I'm
Oh,
saying.
okay.
So let me rephrase. We're gonna do it. Oh, okay.
Okay.
So
Got
now before we do that, I'm gonna redo this one if I had drawn a standard XY. I know this is useful in chapter 6. So why not learn it? Because chapter
right.
6 is on your final. So I'm not just trying to waste your time with that. But that said, remember, this is 2/3 of these problems. FBD correct. You can see it takes a lot of time and effort. And then this one. So one of the things I did in Canvas was I literally drew pictures and I said, which one of these is the correct FBD? So you have to go through and pick the arrows. And one of them is which is the correct component of weight in the horizontal direction if this is your coordinate system. And so I chose a bunch of weirdo coordinate systems, and you literally have to look at the coordinate system and say, is it going to be mg cos? Is it going to be mg sine? Is it going to be positive? Is it going to be negative? That kind of thing. So what we're doing right now, you will be quizzed on. And I don't know if it's in the chapter 5 quiz or chapter 6 quiz or both, but you're going to be quizzed on the stuff that we're doing right now. So that's another reason I'm like, why don't we just do it so you know your shit? All right.
So whenever
Yeah.
you're flipping your coordinate system, do you have like a strategy like where you like line it up with the natural force kind of? Because I noticed that like,
Normal force. But
normal force-
yeah. So usually what you do is this. You look at the picture and you have some force vectors and an acceleration vector. You usually pick the coordinate system which lines up with the most arrows. In this case, this coordinate system lines up with 2. If I had done standard XY, it would have lined up with 2. So it doesn't matter in this problem which, right? The more sine and cosine crap you have to split up, the more likely you are to screw up and switch a sine or a cosine, the more likely you are to make a mistake. So by always doing these problems this way, you get 2 benefits. One, usually blocks accelerate either up or down the plane, and that means you never have to split up acceleration. 2, as was just noted, you never have to split up the normal force. And so what happens is by doing the problems the same way over and over again with this rotated coordinate system, generally speaking, okay, I don't split up these, and you only have to think about these. You get a lot of practice splitting up those, and then you reduce your probability of mistakes because you practice the same splitting over and over and over again, and you get good at it, and you're like, isn't this almost always mg sine theta? And so you just reduce your probability of errors by doing them the same way every time. Is that good?
Yeah, so
Yeah,
just
count
to
the vectors.
clarify for like, so
Yeah.
you typically try to like line up one of your axes with the normal force, and then you try to have your acceleration like going like either in the X or Y direction.
I would be careful. I would line up the coordinates with the acceleration. The normal force is a nice side benefit.
Okay.
That's how I would think of it.
The main goal is try to get acceleration lined up with one of the-
because then one of the equations equals 0 and it reduces algebra time.
Okay.
That's the only reason I do that. It's not because it's right. It's just there are many correct methods.
Okay, so is it kind of just like a coincidence that the past two, like the act? Okay.
Yeah.
All right.
Yeah. So good.
Yeah, I'm good. Thank you.
Yeah. In general, as long as you line up the coordinates with at least one vector, you're reducing your workload some, right? Like I could choose this as an axis. How about, oh gosh, I could do some, it's hard for me to, I could pick some arbitrary thing that doesn't match up to any of the arrows, and that would be terrible, right? Because then I'd have to split up everything and have multiple angles and it'd be confusing. So yeah. All right. That said, let's go take a look at the solutions and see. Okay. So there you go. Wait a minute. Is something wrong here? Oh, I see. My angles in this picture just are a little bit smaller than the ones in the. So in actuality, this should be rotated even more, right? The normal force is really more. So I should go in here and rotate this so it looks more like the picture. I used a 30-degree angle. It should be more like a 60-degree. Does everybody see that? But the equations are all correct. Sorry about that. All right, so we get a bunch of stuff. Ugh, boring. Okay, a bunch of algebra, easy. Okay. Now, obviously, I say the algebra is easy. I know for you guys maybe don't have the best algebra chops yet. You will soon. You will soon. Okay, let me make a quick note to myself to rotate that figure 510 a little bit more. Sorry about that. All right. Now, I want to just show you what would happen here. What if we had done this a different way? We know that there's a normal force this way. Same problem still. We're not doing a different problem. I'm just showing you a different way. We know that there is an applied force this way. And there was mg straight down. When I look at just the arrows, you're thinking, why would I ever bother using that rotated coordinate system? Wouldn't this one be a lot easier if I just used a standard XY? Now, keep in mind, in this case, we know that down here, I think it was right about there. This angle was theta, right? So that means this angle up here is what? Is this theta or 90 minus?
90 minus theta.
90 minus. So what's this angle?
Theta.
And wait, if this is, let's see. Oh, wait a sec. You said it wrong.
Okay.
I caught it by looking at the size of it. Isn't theta a big angle? Isn't this a big angle?
Oh, yeah.
By whatever. So this angle would be 90 minus, which means this angle is theta. So what is this one?
That's 90 minus theta.
And so what is this one?
And then that's theta.
Yeah, so now we see that that's the theta up here. Now I don't need this anymore. Did that make sense? It was the alternate whatever from you could tell I don't remember the geometry rules. I just know how to use them. The alternate whatever rule comes up again. All right, so I'm going to split this force up. So this side is going to be, if that's theta, this side is going to be what? N cos or n sine?
And cosine.
Notice there's no point in trying to remember, oh, x gets the cosine, because it's only true about half the time. Literally, half the time you're wrong if you just assume the x component gets cosine all the time. Okay, half the time you'll be right, but half is not enough to pass a class. So, all right. So now this is looking good, right? Let's practice. Let's write the force equations for this. So in the x direction, give me a force. I'm going to make this a little shorter so I can have room. Sorry. What's one force in the x direction here?
And sine theta.
Okay.
Oh,
yeah, sure.
yeah,
N
yeah.
sine theta. And if we're using, I guess I was assuming we'll use the normal xy, right? So if we use the normal xy, would n sine theta be positive or negative?
Negative.
Okay. What's next? Anything else, or are we done?
The force applied to the object.
Is that going to be plus or negative?
Plus.
Anything else for the force arrows?
I think that's it.
Okay, so it's mass. We'll come back to the acceleration in a minute. Let's do the forces in the y direction. What's that going to be?
And cosine.
And I think that's what? Positive or negative here? Positive. What else?
And negative mg.
And this is AY, right? This actually looks pretty easy, doesn't it? Why didn't we do it this way? Because students fail a lot when they try to do it this way. Where's the hard part now?
The acceleration.
Let me ask you a sneaky question. We know this thing accelerates this way. Why is it a bad idea to draw it on here? Why should I not just do this? This is subtle.
Because it's not a force.
It's not a force. It doesn't belong there. People might think A is a force. So I'm going to draw a separate little picture for it. There's the acceleration vector. So which of these is theta, the big one or the little one? Is this theta or is that theta?
The little one?
Look back in your picture. Is theta the little angle or the big angle in this case?
The big one, the big angle.
And so that's what I'm talking about by not drawing it close to 45. Isn't this, do you see that's the second time we've used that? Once was when I caught my mistake earlier. This time we caught another mistake. It's really nice if you draw well and don't use 45 degrees, all right? Okay, so now what's acceleration in the x? Is it a cosine, a sine? What is it?
A cosine theta?
Nope. Why not? You're very close.
Negative a cosine theta?
Yeah, and see what I'm talking about? It's negative a cosine theta. There are multiple ways students can screw up the acceleration. One, it's tricky to get the angle. Two, it's tricky to get the sine. I just want to point out you missed both of them. And so that's why I usually line up the coordinates with the acceleration, because it's easy to screw this one up. I can screw it up too. So you want to avoid screwing it up. The easiest way to avoid it is line up your coordinates with A. All right, so now what's this one down here? So what's the acceleration in the y direction for this one?
Negative a sine theta?
I think you're right. So again, this is going to be a cos to the left. That's going to be a sine. And you got the signs right. But so I want to point out, it looked like it was much easier until you get to there and you're like, ah, it still sucks, right? So, all right. Questions about that? Anything? Again, this is 2/3 of the problem, getting it right. So I said this way looks pretty difficult. Can you think of an application where this would actually be the smart way to do it? This sneaky question. I guess where I'm going with this is, if you're going to try and use a computer, a lot of computers have a default coordinate system that matches the standard XY. For example, if you're going to code a simulation in Python, this is probably the way to do the problem. And then all you have to do is know, oh, well, I need a negative magnitude, right? And so you're going to end up putting in some negative numbers for AX and AY in the computer code. That's not a big deal in a computer code. So that's the idea. Let me see. I know we're out of time here almost. So just to nail this down, I want to show you something. Let me see if I can find it really quick. I wasn't planning on doing this, so I got to open up a different file. Let me show you something here. Let's see. We'll go to here. We'll go. How about? Oops. Let me move this Zoom crap. Okay, so we're doing 161 lab. I just want to show you something. These are some different coding ones. I think it's this one. No, it's not that one. So look at this. This is very similar, except it has friction, okay? And so I just want to point this out. This will show you how to write a simulation if you wanted to. This is kind of the, now this one has friction. We haven't talked about friction yet. So there's a bunch of words here, blah, blah, blah. Ignore that. But I just want to point out, we are good in physics at understanding things in this picture, right? That helps us understand the magnitude of the normal force, the magnitude of the friction. So we can do a problem in the rotated coordinate system to solve for N and F. Give me a second. And then what you do is when you want to code it, you have to code it like this. And this is what the same problem looks like in the code where you split it. So sometimes you literally do both of them. So I'm going to leave it at that. There are times you would do both of those unless you guys have a question about that or whatever. So that we'll do in Physics 161. I'll make you guys code these simulations up. Yeah. All good? Jay, do you have any advice for students as they're going? Let me see if I can get you on the screen here. Whoops. Hold on. There we go. Jay, any advice for students with FBDs?
I prefer to keep the FBD on whatever surface I'm doing. So if you have an incline, I always did it with the incline rather than using the standard coordinate system. I just think that that works better. But if you find that it's easiest to do the normal XY coordinate system, then do whatever works for you. But I find it easiest to do it with whatever surface your ball or your block is sitting on.
Right on. Okay, cool. What about when you were practicing these? Do you have any advice for them? Like, did you do all of the problems all the way through, or did you mainly do setups and then force equations and then stop, or any advice? Or how often did you look at the workbook when you were doing them? Excuse me, the solutions.
So I definitely set up and did the force equations for all the problems.
Did you have the solutions open when you did that, or did you do it by hand then check, or was it a mix?
I do it by hand and then check. So for the first like 2 or 3, I probably did it with the solutions, but most of the time I did it by hand and then checked with the solutions afterwards just to make sure that I had the right concepts.
Gotcha.
But I tried to do it without the solutions first.
Mm-hmm. When you were working, did you have a study partner or were you flying solo?
At this point in the class, I was flying solo and I regretted it. But it is possible.
Yeah. If you have a partner that you can work with, they can help you catch tiny things like, oh, you just missed the minus sign there that you won't see the first time through. And it's not that you don't make the mistakes, but you make more mistakes more quickly and learn from them more quickly. So you have a study group now, right, Jay?
I do have a study group now, and I'm very thankful for it.
How do you guys manage it online? How do you deal with it?
We do a lot of calls over Discord. If we didn't have Discord, we'd be doing it over Zoom, just trying to find ways to communicate.
Yeah. And then you're just, I guess, yeah, it's brutal. It's not the same as sitting in a room and just looking at paper. It's so much harder.
Oh no,
It sucks.
no.
Yeah, yeah. All right. All right. I appreciate that, Jake. Let's see. Let's see what time we're at here. I think. Oh, let me get my clock back on screen. So 12:19. It's about time to go. I'm going to just take a quick look at the schedule really quick. Let me see if I have that one. If you want to take, actually, let's just call it a day. Because I'm not sure. Yeah, if you want to take off, I'm just going to look up the schedule and see how many more days we have of this. That's all I'm doing. So if you want to take off, that's, oh, I forgot to share screen. My bad. Yeah. Yeah, it's hard to deal with the work. So let's see. I'm just going to quickly check your schedule really quick. Find out when the next quiz is. That's all. We did chapter 4. So the next quiz is November 4th. Okay, so we've got the 26th and the 28th. We're probably going to hit Newton's third law on the 26th. The 28th, we'll just do mixes of problems that have Newton's third law in them and weird angles. And then the 2nd, we're going to move on to chapter 6. And then the 4th will be your quiz. So that's kind of a schedule ahead. And now I can stop the live stream.